All right, to clear a little between oxidation and reduction, let's go with a few definitions and examples to make sure that you understand what different definitions of oxidation mean and how do these different definitions work for us for different questions in exams, right? So what we're going to do is that we're going to start with the very basic of oxidation and reduction, and we are going to quote all the definitions on the same page so that it's not difficult for us to understand all of them in one single go. So starting off with oxidation, the first definition that we understood was addition of oxygen. If we add oxygen to something, any chemical, any substance, it would be oxidation. For example, we have nitrogen gas and we react it with oxygen gas. The product is formation of nitrogen oxide. Nitrogen oxide is actually the oxidized form of nitrogen, right? This reaction would be catered as oxidation reaction. Why? Because
Yeah.
we're adding oxygen to nitrogen. Now, in order to further explain, the exact opposite was reduction, removal of oxygen, or taking oxygen out. Different words may mean the same thing and actually may explain the same definition. So let's say if something has oxygen in it and we remove or we take it out, let's suppose iron has oxygen in it and it's in the form of its oxide, we react it with carbon and we get pure iron and then we get carbon monoxide. So iron previously had oxygen. We took oxygen out of iron, so we got pure iron after. So this would be then reduction reaction, right? So in this
Yeah.
case, I'm specifying that this case of iron oxide to iron would then be reduction reaction, okay?
Yeah.
But not every reaction has oxygen included in it. What if a reaction has no oxygen being added or being removed from it will then be actually bound to not call them oxidation or reduction? So that won't be true. So we needed to come up with other kind of definition to still call the reactions as oxidation or reduction reactions, even when they never involved any oxygen. So another way of defining it was loss of electron. So loss of electron from a compound, from an element, from a species would then be considered as oxidation. And another definition for reduction would be gain of electron. This is the main definition of um, oxidation or reduction that we go for. I'm using E negative signs. If you don't want to use them, you can simply write the whole word electron on both sides, and this might make easier for you to understand what we are talking about. Now, in this case, the explanations are pretty easy. Let's say sodium is a metal. It can be converted into a sodium ion by removing one electron, the exact same thing that happens in ionic bonding. In ionic bond, usually one element, most of the time it's a metal, loses an electron. On the other hand, there is another element, most of the time it is a non-metal, and they form different ions. Formation of positive ion would then be known as oxidation, this one as an example. On formation of a negative ion, this one as an example would then be known as reduction. So if you notice in both of these reactions, there is no oxygen, but this
Yeah.
still falls under the category of redox or separately speaking, oxidation reduction reaction, right? So we needed to come up with another definition for the kind of reactions which are reduction or oxidation reactions. They don't involve any oxygen in them. Hence, the transfer of electron. So the transfer of electron gives us the idea about the loss of electron for oxidation or gain of electron for reduction reaction. Make sense?
Yeah.
Now, it's pretty easy After you understand the oxidation and reduction parts, it's really very easy to give the reactant some name. I'll be very clear about it. Now, notice, and this time I'm going to use a different color. This is the reactant for oxidation reaction. And since this is an oxidation reaction, we can easily call it a reducing agent. Although this is not a redox reaction, I shouldn't be writing it this way, but this is just to explain how this goes. And since this is a reduction reaction, this specific species, this reactant, can be named as oxidizing agent. All right. Oxidizing agent and reducing agents do exist in the whole redox reactions where there is simultaneous occurring of reduction and oxidation reactions. But just for the sake of explanation, how do we name the reactants in these specific reactions as? It's pretty easy. Whichever one is going through the process of oxidation, in this case it's a sodium atom, so would be a reducing agent. Whichever one is going through a reduction reaction, in this case, a chlorine atom would be an oxidizing agent. Now, this clarifies how we name the reactants for these reactions. And they're actually tending to be the opposite of the process. If the process is oxidation, the name is reducing agent. If the process is reduction, the name is oxidizing agent. So if I mix both of these reactions up on one page, so the formation of an ionic compound is pretty much a redox reaction because the metal loses the electrons, undergoes oxidation, the nonmetal that gains that electron undergoes reduction. And there you go, you have a complete redox reaction to form an ionic substance. In this case, an ionic salt, sodium chloride. Makes sense?
Yeah.
So if you put all of these definitions together on one page and compare them at the same time, this is going to give you a very clearer picture. Doing them separately on separate pages, yeah, there is context one after another, but once you're done with all of it, you can put all of them into a single view, giving you a comparative idea of all the definitions in a single go.
Yeah. All right.
Are we good?
Yeah.
Wait, can we continue with the reaction with dilute acid? I guess this
Yeah.
is dilute hydrochloric acid. Okay, so let's come to our topic for today. And going a little up, this is reactions of metals with dilute acid. This is activity number 4. We're going to perform a practical to investigate into the reactions between metals and dilute acid. Now, in this case, there can be different dilute acids that you can use, but we are going to start off with dilute hydrochloric acid. Now we set up 4 different test tubes, about 2 cubic centimeter of dilute hydrochloric acid into each tube, and we use 4 different metals. As you can see in the diagram, we are using a piece of magnesium, zinc, iron, and copper. It's better that for fair judgment, the pieces are of the same thickness or of same length, or both. So
Sir,
you
what?
put them in.
Sir,
Mhm.
what's the meaning of dilute?
Okay. Dilute is
Yeah.
a word that we discuss against concentrated, and both the terms are actually relevant or comparative terms for one another. Now, these both go for solution, dilute solution and concentrated solution. Now, you already understand that a solution is made up of 2 things, solute plus solvent,
Solvent. Yeah.
right? So there must be a way of defining both dilute or concentrated solutions. So let's take cater a couple of examples. Before we move any forward, I need to clarify dilute and concentrated solution ideas so that can have a very good understanding about it. So if we have um, less solute or if we have more solute in comparison, we may call them dilute and concentrated solutions, provided the solvent is same. Let's take an example to understand what I just said, because without an example, these words might make no sense to you. So let's consider a glass. Let's fill it with water. Usually the glasses of water that we commonly use at home are 250 cubic centimeter water. Now, since you're doing it at home, let's say you add 1 tablespoon of sugar in it, right? For the
Mm-hmm.
fair judgment, you take the same size glass over here, you fill it with equal amount of water, and again, you have 250 cubic centimeter water, and in this glass, you add 2 tablespoons of sugar. I'm using these equipment or using these examples because this is something you can easily perform at home. Now,
Yeah.
imagine and understand in both the cases, I have equal amount of water, but the solute is less in the example of dilute solution, 1 tablespoon of sugar, and it is more in comparison under the concentrated solution heading, which is 2 tablespoons of sugar. And I hope you already clearly understand which one is going to taste sweeter than the other. Of course,
Mm.
that has more amount of sugar.
Yeah.
So we call those concentrated solutions.
All right.
So the first idea, this is not complete yet. The first idea was that dilute solution may have less solute or as compared to concentrated solution, which may have more solute. Now, this is not completed. So let's move forward. Another way of comparing it is that they both have equal amount of solute, but dilute solution can be the one which has more solvent, and this one has less solvent. This is the
Opposite.
second way to, yeah, this is the second way to recalibrate it or understand it. So let's take again the same set of examples. We're going to consider the same glass of water. Since I have less space, I am drawing a bit smaller diagram. Imagine this is 250 cubic centimeter of water over here, and we have 1 tablespoon of sugar in here. And in the other one, I intentionally never filled the glass full, and I intentionally filled the glass half. And for the same 1 tablespoon of sugar, I filled the water half of it, which is 125 cubic centimeter of water. Now, which one do you think is going to taste sweeter than the other?
Um. Sorry, repeat your question.
Which one would taste sweeter than the other?
Concentrated.
Concentrated. Concentrated always tend to be more sweeter than the dilute ones, be it because of having more solute or having less solvent. Both ways, it's going to be sweeter than the dilute
Mm.
solution. And
Yeah.
that's what it means. So whenever we talk about dilute solution, you need to understand the point that this might have either less solute or this might have more solvent to give you this dilute impression. All right.
Yeah.
And if we talk about concentrated, you are going to either assume it with more amount of solute present or more amount of solute and less amount of solvent present to give you the idea. Maybe the
Mm.
same amount of solute and less amount of solvent.
Yeah.
Are we
Okay.
good? So that's
Yeah.
how we refer to dilute and concentrated solution. Now let me explain something over here. Dilute and concentrated are relative terms. These are used for comparison when you have two different things in front of you and you can compare them. But they can also be used as absolute referring. Absolute referring means you don't have to compare it with anything because you know the generals. right?
Yeah.
Okay, for example, if somebody, if say, let's say, if there is an adult male and he has a height of 6 feet, then we might not call him having a good height. But if someone has 7 feet height, we definitely will call him the person with the greatest height in the class, probably. Why would we do that? We understand that we're not comparing him with anyone, but even if we did, this is definitely more than the average. So he's going to stand taller than all the other people in the class. So that's why we do it. Now, the point I'm trying to make is that he is saying dilute hydrochloric acid over here without even giving you any other comparative idea. So the examiners do tend to put dilute in concentrated words in exams without referring to a comparative counterpart. They do it for the sake of your understanding, right? So this would give you the
Mm-hmm.
idea that we have less amount of hydrochloric and acid and we have more amount of water, right?
Yeah.
It should give you this idea. So this dilute term would give you either one of these ideas, and you understand what this dilute, absolute dilute term means.
Mm-hmm.
I
Yeah.
hope it gives you the idea
Yeah.
clearly. Okay, good.
Yes.
So if we move forward, we were actually talking about taking four different metals, magnesium, zinc, iron, copper, putting them into the test tube, observing reactions. Now, metals tend to produce a little bit of fizzing. They give out gas in the form of bubbles, and you can always test them with a lighted splint. As squeaky pop sounds indicate the presence of hydrogen gas. This is an experiment. Now, if you notice a little bit closely, you would see some bubbles in these diagrams. Notice you have so many small bubbles over here, and I'm not drawing them. These are already drawn, but they are a little faint, so I am actually uh, recoloring them. Can you see
Mm.
that? Now,
Yeah.
if I recolor all the bubbles in here, you'd notice that we have many less number of bubbles in case of right. So these bubbles or this fizziness or the amount of fizz that comes out gives you a pretty good idea which one is more reactive, which one's less. Now, if you start comparing all of these, starting from the left all the way to the right, you'd understand magnesium is the most reactive one. Then comes zinc, then comes iron, and copper is the least reactive one, producing the least amount of fizz.
Yeah.
Make sense?
Yeah. Yeah.
Okay, let's compare the text we have at the bottom of the diagram. So if we talk about magnesium, what you're going to observe is that it reacts vigorously with a lot of fizzing. A good amount of gas is produced. It gives you a quickie pop with a lighted splint. A colorless solution is formed. The test tube gets hot. Now, zinc gives a steady reaction, not vigorous, but a steady reaction. It gives fizzing. Enough gas is eventually collected to produce a squeaky pop with the lighted splint. A colorless solution does form. The test tube gets warmer, not hot, but warmer. Talk about iron, slow fizzing. Little gas is collected. A pale green solution is formed. Iron gives the colored solution, that's understandable. The test tube gets slightly warmer, not hot, not warmer, slightly warmer. Copper gives no change. Might be a bubble here and there, but not enough gas. You can't test it with a squeaky pop. There is no permanent fizzing, and you might not be able to test the change. The test tube won't even change. It won't get hotter. It won't get warmer or even slightly warmer. Now, there are many observations that we are giving to you at the same time. Let's talk about them. The fizzing is due to the gas formed. The gas is hydrogen gas, so we can test it with a squeaky pop if we have enough gas. You do collect enough gas for magnesium and zinc, but you don't get collect enough gas for iron. You don't able to. You're not able to collect some gas for copper even. Now, The solutions are usually colorless for normal metals, but for the metals that are present in the center of the periodic table, the solutions are usually colored, iron or copper being one of them. Copper does not react. If it reacted, definitely gave a colored solution. And at the end, test tube either gets hot or warmer or slightly warmer. That's because the reason written over here that these reactions are known as exothermic reactions. The word exothermic thermic literally means giving out heat. We're going to study this specific change in chapter number 19 in detail, but so far you notice that there is a change in temperature, because of which some test tube may get hot, some may get warmer, some may get slightly warmer. Definitely, there has been a change of temperature or heat. Make sense?
Yeah.
Good. If it does, let's move forward. Now, in order to have been careful about things, remember it should be a valid or fair test. So the volume and concentration of hydrochloric acid are the most obvious things we have to keep same. Mass of the metal, right? Which also includes the thickness and the length of the metal. Okay, so that's important. Now, mass of the metal is a more difficult question because when we convert these masses into our standard units, mole, this come out as a problem. Now, since you haven't done this mole calculation chapter, so I'm skipping these lines intentionally because you won't be able to understand them until unless you're done with chapter number 6 and 7 in the first unit of the book.
All right.
Okay, so the other variable we should control is surface area of the metal. Although this does not affect the overall amount of heat given out in the reaction, but it does affect the speed at which the heat is given out. For example, if you're going to use one big piece, you are going to go for a slower reaction. If you use small pieces, it would be a faster reaction. If you use finely divided or powdered form of the metal, it is going to give you an extremely fast reaction. So we use the following procedure to investigate this reaction quantitatively involving numbers, measure out a specific amount and concentration of hydrochloric acid using the measuring cylinder, right? Now this amount is chosen so that the acid is in excess. There is more than enough of the acid to react with all the metals. Pour the acid in a polystyrene cup. These are the white cups that we commonly use for beverages. We use the same white cups because these are insulating cups. Polystyrene is an insulator. We'll study it at the end of this book. So we use this cup so that the heat doesn't go out. Heat is not dissipated so quickly. We measure the initial temperature of hydrochloric acid, weigh out a specific amount of magnesium powder, add the powder to the cup, stir it rapidly, measure the maximum temperature reached because temperature is definitely going to change, repeat it with other metals using the same amount or unit per metal at a time. Notice that the data of this experiment could be this much amount of magnesium with this initial temperature went to this maximum temperature for zinc, for iron, for copper. Now notice the maximum temperature is something that you can relate to. Most reactive metal goes to the higher temperature change as possible, as high as possible. And the least reactive metal does not give you a big temperature change, sometimes no temperature changes at all. Make sense?
Yeah.
This gives you the idea that the temperature change is biggest for the elements that are reactive and least for the elements that are least reactive. So this is how we can work this out. A bar graph gives you a very good idea that the reactive metal gives you a big temperature change. The lesser the reactivity of the metal, the smaller the temperature change. Okay? You don't even see a temperature change for copper being least reactive. Make sense?
Yeah.
So general summary, the pattern for reaction of metal with acid is the same for the reactions of metal with water. In each case, the reaction is much more vigorous for a reactive metal and least vigorous, or you can't even use the word vigorous. The reaction is least for the least reactive element. Okay, so the metals that are above hydrogen in the reactivity series, they react with acid, they form a salt, and they give out hydrogen gas. The gas we just tested with a squeaky pop. So the higher the metal in the series, the more violent the reaction. Notice
Yeah.
metal plus acid gives you salt plus hydrogen. If you're doing it with dilute sulfuric acid, it is going to give you a sulfate salt. If you're doing it with a hydrochloric acid, it is going to give you a chloride salt. But definitely, it would give you a salt, metal salt every time, plus it's going to give you hydrogen. We use a mnemonic MASH for it. Metal, acid, salt, hydrogen. Metal, acid, salt, hydrogen. MASH. Makes sense? So MASH is a
Yeah.
good way to remember. But this goes for metals above hydrogen in the reactivity series. The ones that are below hydrogen won't even react with them. Okay? And I
Yeah.
hope this you already understand from copper. See, copper is not even reacting, not even producing heat. Why do you think it is doing that? Let's go a few pages back. Now, notice in our reactivity series, hydrogen and copper is right below it, which means copper will not react to produce hydrogen gas, silver will not react to produce hydrogen gas, and so does gold. Anything below hydrogen will not react with acids and will not produce any hydrogen gas. Make sense?
Yeah.
That's why copper wasn't even reacting in this reaction. That's why copper was not giving any kind of temperature change in this reaction. So metals below hydrogen in the reactivity series, copper, silver, gold, do not react with simple dilute acids such as sulfuric or hydrochloric acid. Are we good?
Yes.
Okay. So for potassium, sodium, lithium, and calcium, the most reactive metals on the reactivity series, they are too reactive to add safely to what I said. The reaction is too violent. Calcium can be used if the acid is very dilute, but you cannot use it with dilute acids. You cannot even think about using them with concentrated acids since the reaction is too violent. All right.
Yeah.
So when you're writing answers for exams, keep something in mind that you won't be able to use it as a safe experiment. It is always going to have hazard. So make sure, even if it's asked as a question in exams and you're talking about it, make sure you mention the safety issues with these reactions. And never, uh, as an answer or your argument in the answer, recommend these reactions because these are not safe. So, metals from magnesium to iron in the reactivity series, let's go through that. Magnesium reacts vigorously. See, it's forming a sulfate salt, hydrogen. If it was hydrochloric acid, it would have formed a chloride salt like this. So Mg plus 2HCl gives us MgCl2 plus H2. So you see we have a chloride salt in case of hydrochloric acid, we have a sulfate salt in case of sulfuric acid. That's how the acid actually drives the reaction
Uh-huh.
and the kind
Yeah.
of salt produced. So aluminum is after magnesium. Of course, it would be a slower reaction than magnesium. But after warming, it can react very vigorously. Thin but strong layer of aluminum oxide on the surface of aluminum would be produced. This would stop the acid from getting it further reaction. On heating, we can remove this layer. Aluminum can show its true reactivity, and this is how it proceeds. So, with a chloride based or hydrochloric acid, it produces a chloride salt. So, I hope you understand from this. Any metal they pick for their examples, you should understand that you should be able to come up with a salt. Now, for example, they're talking about zinc and iron. So if zinc reacts with sulfuric acid, it forms a sulfate salt. If iron reacts with hydrochloric acid, it would form a chloride salt. But in both the cases, hydrogen gas would be formed, as stated above. And you can see the diagram too. zinc reacting with hydrochloric acid, producing a lot of bubbles. Sorry, iron reacting with hydrochloric acid. Okay. Now,
Yeah.
iron being a transition element may give you this or this ions. So they can produce two salts with iron 2 ions, or they may produce three salts with iron 3 ions. So iron actually give rise to two possibilities. Okay.
Yeah.
Now, finding the approximate position of a metal in the reactivity series. Now, your reactivity series is very limited. See, I'm going to go a few pages back and I'm going to explain myself what I meant from saying it. Now, go ahead and count the elements in the reactivity series. So you start from the potassium. This is 1, 2, 3. This is 4, 5, 6, 7, 8, 9, 10, 11. You have a total of just 11 elements in your
No,
reactivity
sir.
series. Yeah,
Sir, it's 12. Oh, acha, metals. Okay.
metals. Okay. So what if you want to add any other metal to it? There are many more metals in the periodic table. There are more than 70 elements in the metals in the periodic table. So what if you want to add another one? How would you know the position of that metal? Where are you going to place it? Let's suppose you want to add, let's say, lead, another metal. Now, how would
Mm.
you know whether lead to be placed in between magnesium and aluminum, or between carbon or zinc, or between zinc and iron? Where would you place it? You won't know until unless you perform a few experiments. And that's how we cater it. So let's go back to the place and discuss it. So if you have a metal, add a very small piece of metal to some cold water. See the observation. Is there a reactive rapid reaction? If there is, it should be above magnesium. If there isn't any reaction, add a small amount of metal to some dilute hydrochloric acid. If there isn't any reaction in cold acid, warm it carefully. If there is still no reaction, the metal is probably below hydrogen. If there was some reaction, the metal should be placed in between magnesium and hydrogen. So it's pretty easy, right? Let's go back.
Yeah.
It's a little bit difficult when you understand it without the reactivity series, but if you have the reactivity series, it's pretty easy. So all of these react with cold water. So if your unknown metal reacts with cold water, you need to put it above magnesium. All of these do not react. These do not react with dilute acid. All right. So if your element do not react with dilute acid, that is probably below hydrogen in this reactivity series, right? If
Mm.
it does not react with cold water, but it does react with dilute acid, it means it needs to be placed somewhere in between magnesium and hydrogen. So that's how we have a guess. So reacting it with cold water or with cold dilute acid or warm dilute acid gives you a very good idea where you can place your element. Make sense?
Yeah.
So moving on, if we continue on the same path and make predictions, let's say manganese, Mn, is an element. Okay, it lies between aluminum and zinc. It forms a +2 ion. The solutions are usually pale pink, almost colorless. So we use the reactivity series to predict whether manganese will react with copper 2 sulfate solution. If it will react, what are the products or equation you can see? Explain why do you expect manganese to react with steam? Name the product or write the equation. These are the kind of questions that you may be asked. Now, if you're talking about the first question, reaction of manganese with copper 2 sulfate. Now, we are putting manganese over here, right? There we have copper. Manganese is definitely on top, copper is at bottom in comparison in the reactivity series. So yeah, if this reaction would go ahead, manganese can displace it. So manganese will displace copper out of the sulfate, will form manganese sulfate and put copper away as a separate element. So the displacement reaction would occur. Make sense?
Yeah, it's easy.
So this means you should be capable of writing this equation on your own.
Mm.
Okay.
Yeah.
Now, the reaction between manganese and steam. Would manganese be able to react with steam? Now, we already know with steam, they form oxides and hydrogen. So form manganese oxide and hydrogen. That's about it. That's all you need to do.
Mm. All right.
And since we are putting it right below magnesium with a difference of one or two elements, it won't react with cold water, but it would definitely react with steam. Hence the reaction possibility as well as the product. So from the position, we can predict the properties, or from the properties, we can predict the position.
Uh-huh.
I hope this clarifies it.
Yeah.
All right, great. Just rusting of iron, one of the last topics of the chapter. Iron rusts in the presence of oxygen and water. This happens naturally to iron. Rusting occurs with iron and the most common alloy of iron, which we call mild steel. Now, the formula for rust is Fe2O3, and there is some variable number of water molecules with it. We call it hydrated iron trioxide, right? Hydrated because it has water along with it. X means there can be different number of water molecules with it. It can be just one water molecule, it can be two, it can be three, it can be more. Hence
Mm-hmm.
the letter X. Now, this is commonly also known as corrosion. If it occurs to any other element, corrosion. If it occurs to iron in specific, rusting. So hence this hence corrosion and rusting. Now, they have clearly explained this happens due to the oxygen in the environment and water vapors in the environment. And this changes the appearance, the color, the everything that iron has to offer. Forming rust from iron is a surprisingly complicated process. Iron loses electrons, it forms ions, they're then oxidized by air to form iron 3 ions. Reactions involve water, produce the actual rust. So this means water is going to be responsible for it. And since we are going with loss of electrons, this is an oxidation reaction. Now, clearly, previously it was just iron. Now we have oxygen added to it. So that defines the oxidation, right?
Yeah.
Remember, loss of electron or addition of oxygen, both were oxidation reactions. Now, how can we prevent rusting? Now, the rusting can be prevented by a number of methods. The first, most common method are barriers. Barriers is to keep either water or oxygen or both away. You can paint the surface of iron. Water and oxygen will not be able to get to iron. You can coat it in oil, you can coat it in grease, you can cover it in plastic. These are all barrier methods. The painting layer, the oil coating, the grease coating, the plastic actually creates a barrier and does not allow water or oxygen to pass, hence keeping the iron safe. These are actually cheap ways of preventing rusting. Why do we tend to prevent rust? Because the strength of the metal is lost during rusting. Now, we clearly use iron in our bigger structures like uh, uh, this kind of chain that you can see is commonly used with ships. Now, this chain has very important purposes to cater. So, if it is rusted, it will slowly break away. And when chains like this are broken down, or iron as a part of a structure is broken down, of course, it is going to collapse. And this can
Mm-hmm.
come as a problem. So, barrier methods are usually cheap. They keep iron away from rusting, so we don't have to go with loss. The second one is galvanizing. Galvanized iron is an iron which is coated with a layer of zinc. Now, let's suppose this is a piece of iron. What do we do in galvanizing is that we actually give it a fine layer on all sides. My layer is not as fine, but from all sides with zinc, right? Now, if you go back to the reactivity series, you'd understand that zinc is up top and iron is comparatively on a lower position, which means zinc is more reactive, which means when it would be exposed to air and water, zinc would react and will not let iron react, which means zinc is going to keep iron safe because it will not let it react.
Uh-huh.
So even if you expose the surface, zinc is more reactive. It reacts with oxygen or water more readily, so zinc corrodes and iron stays safe. In this corrosion process, zinc tends to lose electrons and form ions, and they don't let iron do the same. So iron does not get rusted, zinc does, right?
Mm.
Another technique would be sacrificial protection. Now, we sacrifice a more important or more reactive element just to keep iron safe. Zinc, magnesium, aluminum, these are all more reactive than iron from the reactivity series. And just to prevent iron from rusting, we can use any of these in the form of blocks. We commonly do it on ships, right? We do it in such a way that we put blocks of either zinc or magnesium or aluminum and we prevent iron. So these are
Mm.
sacrificial nodes. Sacrificial nodes have to be replaced occasionally. When more reactive metal has been completely oxidized, the iron will start rusting. So what do? We replace them regularly. So actually, galvanizing was a combined method of barrier and sacrificial protection. Sacrificial protection is simply sacrificing a more reactive element to save iron. Now, in all these cases, the more reactive element would rust or will get corroded and iron will not. I hope this all makes sense, right?
Yeah.
Good. And that's it.